This is the notebook for the video, dissecting one of the most used loss functions in deep learning, cross-entropy loss. To recap, entropy assigns a number to the information content in an event. High probability events have low surprise value, or low entropy. Low probability events have high surprise value, or high entropy. Numerically, the entropy of an event is the negative logarithm of its probability, where the logarithm base is 2. The entropy of a probability distribution, on the other hand, is the sum of the entropy of the individual events, weighted by the probability of those events. The goal of this notebook is to illustrate the underlying reason for why cross-entropy, which is explained below, is used as a loss function. Imagine a model is learning to predict the distribution for some input. For example, the model predicts 80% cat and 20% dog for the image above. Let's use these predictions to compute the entropy of each event, and then weight the entropy of each event by the true probability of that event, say 90% for cat and 10% for dog in the image above. This value we computed, also called cross-entropy, will be lowest only if the predicted probabilities are the same as the true probabilities, which is not, in this case. That is, cross-entropy is lowest only when the predicted distribution is the same as the true distribution for an input, which is 90% cat and 10% in our example. So cross-entropy, which is a single number, captures how far off the model's predicted distribution is from the true distribution. Closer the probabilities of the predicted distribution events to the corresponding event probabilities in the true distribution, lower the cross-entropy value. Let's understand cross-entropy loss with a concrete example. Let's start with the true probability distribution for the example image above, which is 0.9 for cat and 0.1 for dog. We will come back to the function implementing cross-entropy loss later. Let's compute cross-entropy when predicted and true probability distributions are the same. We will see in the next step that this is the lowest possible value of cross-entropy for the true distribution 0.9 and 0.1. Now let's compute cross-entropy for cases where the predicted probability distribution is not the same as the true probability distribution. Note all the values of cross-entropy computed above is larger than the entropy of the true distribution. This fact makes cross-entropy useful as a loss function. As mentioned earlier, cross-entropy, which is a single number, captures how far off the model's predicted distribution is from the true distribution. Going back to the cross-entropy function, the first part of the function checks if the input's probability distributions are valid. This is done by making sure all the event probabilities add up to 1, are non-negative, and are not 0. The last line in the function computes the cross-entropy, which is weighting the entropy of each predicted event with the corresponding true probability of that event. Cross-entropy loss is used in deep learning models for any classification task, whether it is over 2 classes, multiple classes, or multiple labels. In all these classification tasks, the model is trying to predict a probability distribution. Cross-entropy captures how far off the predicted distribution is from the true distribution. Cross-entropy loss is also used in autoregressive tasks, such as language modeling. For example, ChatGPT learns by predicting the next word in a sentence, given the previous words. Cross-entropy loss is suitable here because it effectively measures how well the model's predicted probability distribution over all the words in the model's vocabulary aligns with the true distribution. As a concrete example, consider the sentence, "She fell." Let's assume the model predicts the word "and" with the highest probability and the word "down" with a lower probability. Assume the actual word in the sentence is "down." The true distribution assigns probability 1 for the word "down" and 0 for all other words in model's vocabulary. So the cross-entropy loss would only have one non-zero term, which is for the word "down." Since the true probability of that is 1, the cross-entropy loss would be the negative log of the predicted probability for the word "down." Closer this predicted probability is to 1, lower the loss. Further the predicted probability of the word "down" is from 1, greater the loss. In summary, cross-entropy loss essentially captures the error in a model's prediction in a single number, which is then used to nudge the model's parameters to make correct predictions during training.